Okay, so this is the second video in the set that corresponds to the second in-person class. And at the end of the last video, we introduced the Schrodinger equation and said that this describes a wave function that's going to tell you the probability of finding a particle at a particular place at a particular instant in time. And that the Schrodinger equation determines the behavior of the wave function by relating the time derivative of the wave function, how it changes in time, to the total energy of that wave function. There's a term that has to do with the kinetic energy and a term that has to do with the potential energy. This tells us that we need to think about analyzing the motion of quantum mechanical objects in terms of both probability and energy. So when we analyze the motion, we need to think primarily about the energy of the object we're describing. And the end result of this is going to be a function that tells us probabilities of finding the particle in a particular place at a particular time. So we can imagine a particle-like object. Here's a ball that I have lying around. And we can think about what is the motion of this going to be like. But to do that, we need to recast it in terms of the energy of the object, and we need to recast it in terms of probabilities. So what does it mean to do those things? Well, let's think about a very classical, familiar situation like a bouncing ball, right? So I have a ball that goes up in the air, comes back down, right, and hits the ground and bounces and repeats that motion, right? So if we look at a bunch of snapshots of the motion of that ball over time, we see that it rises, right, going slower and slower as it goes up, and then it turns around, falls back down, accelerating as it falls, hits the ground, and then repeats that process again. Okay, this is a very familiar sort of thing, right? If you've taken physics in high school, you've plotted out, the trajectory of the ball as a parabola. You learn some maybe projectile motion formulas to calculate how far is it going to travel, all that kind of thing. Right. We want to think about this first in terms of analyzing this motion in terms of the energy. Okay, so I'm going to make a graph here of the energy as a function of height. And this essentially involves taking this bouncing ball and sort of turning it on its side. So higher points are points to the right? And the vertical axis here is going to be the energy of the particle. All right. So what does the energy of this look like? Well, we can look at the kinetic energy of this, for example. The kinetic energy when you're near the ground, right, is going to be quite high because it's moving very fast when it's low down. And it decreases as you go to higher heights, right? So as it moves up, it slows down, comes to a stop for a split second at the top of its motion, then falls back down, accelerating as it goes, right? So the kinetic energy as a function of height is going to be a linear decrease, right, as it comes down. The ball slows down as it goes up, losing kinetic energy, then speeds up as it falls, gaining kinetic energy. All right, what about the potential energy? Well, the potential energy is going to do just the opposite, right? Near the ground, it has no potential energy anymore. It's at ground level, it's turned all of its potential energy into kinetic energy, and as it goes up, it gains potential energy, right? As it loses kinetic energy, it gains potential energy because that instant at the very top of its flight where it's motionless, all of the energy there's zero kinetic energy, there's only potential energy. If you let it go, right, it has the potential to turn that energy into kinetic energy as it falls. All right. The other thing to notice on this graph is, right, when it hits the ground, right, at that point the potential energy becomes absolutely enormous because it's interacting extremely strongly with the ground there, right? And that's what stops it, right? It can't go any farther down there because it doesn't have enough energy to burrow its way through the ground through all that potential energy barrier, and that will become important a little later on. Now, if we look at the motion of this, right, we can take the potential energy and the kinetic energy and add them together, right? And remember, in the Schrodinger equation, that's what we're going to do. We're going to think about the total energy as driving the change in the wave function. When we add those things together, we find that the total energy is a constant, right? Everywhere that we look, where we would see this particle, its sum of kinetic energy plus potential energy is the same. And this leads to an interesting thing, that you can define the turning point, the point where the ball comes to a stop instantaneously and then starts falling, as the point where the total energy, kinetic plus potential, is equal to the potential energy, right? When all of the energy of the ball is potential energy, then it has no kinetic energy, it's not moving. And that's the point where it's going to turn around, right? That's the point where it's reached its maximum height, and from there it's going to fall back down, turn that potential energy back into kinetic energy. So that's analyzing the motion of a ball in flight in terms of energy. What about in terms of probability, right? We're going to end up with a wave function. We want to be able to describe that wave function in terms of probability. So what does the probability look like for this bouncing ball as a function of height? Well, there's sort of two things to notice. There's two sort of shaded areas here, right, where you don't expect to see it at all. You expect the probability to be zero, right? It's not digging into the ground because it doesn't have enough energy to overcome all that potential. And once it's turned all of its energy into potential energy, it can't go any higher. So there's sort of an upper bound on where it could be found. So there's shaded gray regions or places where the probability should be zero, right? In between those, what does the probability as a function of height look like? Well, it looks like this. It's this slowly rising curve that then, reaches a spike and then crashes down to zero above the maximum height. If you look at this, this might seem like kind of a weird shape, but if you think about it a little bit, it makes sense, right? If I imagine taking a snapshot of the ball in flight at different, take snapshots at different heights, I can ask, what's the probability that I find the ball within a particular band of heights? And that probability is going to be maximum up at the top of the flight, where the ball is moving very, very slowly and coming to a stop. It spends most of its time up near the peak of its flight before it turns around and comes back down. On the other hand, if I try to look for it somewhere in the middle of its motion, then it's moving pretty briskly through there. And when it's doing that, it doesn't spend much time in the same width band right in the middle of its motion. When it's moving quickly, it passes through very, very fast, and there's just not that much time that it's going to be found there. There's not much probability of finding it in the middle. So the probability as a function of height for this is going to start out very low near the ground. It goes up and it increases very sharply to a peak at the location of the maximum height, and then crashes down to zero for heights above the maximum, because once you've turned all of your energy into potential energy, you can't go any higher, right? And so that's the classical turning point. Anything above that is forbidden, right? The ball is not allowed to be anywhere up there. And so this is how the energy constrains probability, right? So this is for a classical system, a bouncing ball like a football, like I've got in the little cartoons here. This is how you can use energy concerns to understand issues of probability, right? The energy tells us, if I know the total energy, I know that it's going to be moving very fast near the ground. It's going to be moving very slowly at the top. There's a maximum height it can reach. It can't go into the ground because it doesn't have enough energy to dig its way in there. And so its range is bounded by these concerns having to do with energy. And then within that range, we can talk about the motion of this ball in terms of the probability of finding it at any particular height through the course of its flight. This isn't the kind of thing that we normally do with bouncing balls, but this is absolutely the kind of thing that we have to do when we talk about things that are quantum mechanical. And so it's worth going through it for something familiar before we look at what the quantum analog of this is for, a quantum mechanical ball that's bouncing back and forth under the influence of gravity. How that looks is the next thing we want to talk about, but I'm going to save that for the next video, so come back and check that out there.